Welcome back. I'm Travis with Linux Academy. In this lesson, we're talking about some of the security best practices around Docker. At the very basic level, there are things that we can do at the operating system level to go and help make things more secure, as well as Docker-specific technologies. Docker containers are very similar to LXC containers. They have some very similar security features. Whenever you go and create a container by executing docker container run, Docker is going to go and create a set of namespaces as well as control groups for that container. Namespaces provide isolation for the container. This means processes running within that container cannot see or interact with processes running on the host operating system or in another container. This also gives each container its own network stack. What this means is each container does not have privileged access to sockets or interfaces on other containers. This also means that containers can go and interact with one another using their network interfaces. This is just like any other computer on a network. When a Docker container is created, it's going to get its own namespaces for the process ID, PID, network, net, file system mount, inter-process communication, IPC, user, and UTS. This collection of namespaces is what we call a container. Control groups, also known as C groups, are responsible for accounting and limiting resources on a container. It's also responsible for making sure that each container gets its fair share of resources. This includes CPU, memory, and disk I/O. C groups are also responsible for making sure that a container can't go and exhaust all the resources on a Docker host, therefore bringing the system down. By default, containers don't have any resource constraints. This means they can consume as many resources as allowed by the kernel scheduler. One of the problems that we face when running containers is that we typically don't want to run them as root, because root is pretty powerful and it can be very, very dangerous. However, if we run it using a non-root user, it can become pretty useless. And in order to go and solve this problem, this is where capabilities come in. The root account is made up of a long list of capabilities. Docker works with these capabilities so the container can run as root, but strips out some of these capabilities that are not needed. Also, if a capability has been removed, Docker will prevent the container from adding it back in. Docker works with two of the major mandatory access control systems, AppArmor and SELinux. AppArmor, or Application Armor, is a Linux security module that is responsible for protecting the operating system and its applications from security threats. Security Enhanced Linux, or SELinux, is a Linux kernel security module that provides a mechanism for supporting access control security policies. And the last of the Linux technologies is Secure Computing Mode, also known as SecOp. SecOp is a Linux kernel feature that allows you to go and restrict actions available within a container. Every container is given a default SecOp profile. This profile can be overwritten during container creation. Probably one of the easiest ways of going and securing Docker is to run it in swarm mode. We'll go over this in a little bit more detail in another slide. Docker security scanning is currently available with private repositories on Docker Hub or the Docker Trusted Registry on-premises solution. This solution helps identify code vulnerabilities within your images. It does this by performing binary level scans of the Docker image, and then checks it against a database of known vulnerabilities. Docker Content Trust, or DTC, allows you to verify the integrity and the publisher of an image. This is how you know that an image coming from Nginx is actually by Nginx. This also allows developers to go and sign their images before pushing them to Docker Hub or to a trusted registry. Docker Secrets allows you to go and store sensitive data such as passwords and API keys. Prior to Docker 1.13, there was no standard way of maintaining secrets within Docker. You had to use a third-party application like Consul and Vault. Now, before we move on, I want to quickly revisit namespaces. The PID ID namespace isolates the process tree of each container. It prevents the container from seeing or accessing the process tree of other containers or the host that it's running on. The net namespace provides each container with its own isolated network stack. This includes things such as the network interface, IP addresses, port ranges, and route tables. The mount namespace gives every container its own unique isolated file system. This prevents the container from accessing mount namespaces of the Linux host or other containers. The IPC namespace is used for sharing memory access within a container, and it also isolates it from other containers. The user namespace allows you to go and map a user inside of a container to a different user on the host. A good example of this is mapping the root user of a container to a non-root user on the host. The UTS namespace provides each container with its own unique host name. The easiest way of adding an additional layer of security is by having Docker run in swarm mode. This gives us the following features: cryptographic node IDs, mutual authentication via TLS, secure join tokens for both worker and management nodes, a CA with automatic certificate rotation, encrypted cluster stores, as well as encrypted networking. Now, before we go and close things out, I want to cover the high-level workflow of how secrets work. First off, secrets are only available to us in swarm mode, and this is because of the encrypted cluster store. When we go and create a secret, it is posted to the swarm. It gets stored in the encrypted cluster store, and again, this runs on all the managers. We can then go and create the service that is going to be using the secret and have that secret attached to it. The secret is encrypted in flight when it's delivered to the replica task. The secret is then mounted into the container of the service as an unencrypted file. It's going to be found in /run/secrets. This is a in-memory tempfs. This means that each secret is going to be mounted into the container using its own tempfs file system. For example, let's say we have a secret called mySecret. It's going to be mounted in the container under /run/secrets/mySecret. Once the replica task is complete, the in-memory file system is torn down and then the secret is flushed from the node. Coming up in the next lesson, we're going to start working with some of these security practices. Go ahead and mark this lesson complete.